Okay, welcome Thomas, and welcome all of you who are watching this as an archived webinar. So this is the penultimate webinar, which means second to last. And we'll be talking about chapter 12 today, which is regression analysis, which is a really, really important topic used everywhere. So hopefully you've seen a little of it, and we're going to get into more details and in depth than you've probably ever seen today and throughout the whole week. So just a couple reminders. The first one is your project is due Sunday. And by tonight, so hopefully tonight means Wednesday, by the way, not tonight whenever you're watching it. I'm hoping to get your drafts of your project so that I can take a look at them and then help you out to improve them, and so you can get a good grade on it and get good knowledge about statistics. So again, I'm hoping that I have one in already. I'm hoping to get a bunch more in by tonight, and then tomorrow I'll send them out. Friday's a busy day, and Saturday and Sunday are pretty busy days. So tonight is the time at which you want to make it get it sent to me. After that, you can post on the Q&A on the Project Discussion 2 forum, and I'll be happy to answer questions on the Project 2 discussion forum. Also, 2 weeks from today, your final exam must have been taken. So most people take it that Monday, Tuesday, or Wednesday, which is the 25th, 26th, and 27th of June. And it has exactly the same rules as the midterm exam has. So you will need to let me know where you're going to be taking it. If you're just taking it the same place as the midterm, just say same place as midterm. That's good enough. It's good to let me know when, especially if you're taking it a little earlier, so that I can make sure I get it to the proctor so that it's all ready and situated by the time you're ready to take the final. And if you're taking it in a different location, you need to let me know lots of details, about where and who to send it to and what the website is, so I can verify that they're an actual proctor. But if it's the same place, it's really easy. So that is the big, huge upcoming events coming up. And we have regular work this week, besides the project, we have the chapter 12. We have a discussion post that you have to do, and we also have the assignment for chapter 12. But the biggies are the project and then getting ready for this exam. So, Robert, Thomas, do you have any questions?
No, I don't.
No? Everything's good? Okay. The great thing about regression analysis and a lot of other statistics is I can just, on the whim, bring up something that's important, and particularly important to me, as in Tahoe. And I know, Thomas, I forget, what city are you from?
I'm from Modesto.
Modesto. So you're not from Tahoe, but have you been to Tahoe?
Yeah, I've been plenty of times.
Okay, you've been plenty of times. And you may or may not know, but do you know the most important research that's ever done in our area? By far the most important?
No.
And work is the clarity of the lake. Is that we want to make sure that our lake stays blue and nice and clear and not like an ugly, smelly pond. And if you've been many times, I'm sure you want to keep it that way too. So I thought I'd bring up the researchers that study the clarity of our lake are out of UC Davis. And I thought I'd bring up their data that they've got. And they've got a nice little sheet, and I've got part of it. I got half the story, and then I'll give you the other half the story after that. Okay, so this is the data, and it's a little weird because the y-axis is kind of backwards, and it's what they did because they wanted to make it look like they're measuring it from the top, and then positive numbers are below and how deep you can go. So what they do is every year they take measurements to find out how far you can drop a white dish into the lake and still see it. And this is the data by year on what they came up with up to 1998 or so. So, and the reason I choose this year is the President of the United States came to Tahoe. which is pretty amazing to come to look at our lake and do research when it's the President of the United States. And trivia question, do you know who it was? President of the United States in 1998? It was not Trump, by the way. No, Bill Clinton. Bill Clinton. And in fact, one of my statistics students served him lunch at a restaurant that he ate at. But at the lunch, they showed him this data. And it's hopefully clear to you that there's a trend. Do you see a trend happening? What's happening as the years have progressed?
It's positive.
Yeah, it's actually, and this is a tricky one, it's actually negative. Because remember that 20 is the top and 35 is the bottom. So it's upside down.
Oh, okay.
So I did this because this is what UC Davis shows, not to trick you guys, by the way. I would never trick you guys. I would never give one of those like that on a test or anything. But this is real. And in real stuff, things happen. So this is what happened, but that's okay. So, but there's a clear trend. There's a clear trend. As time has continued from 1968 to 1998, lake clarity has diminished. Do you see that? Okay, and you can kind of see it's a linear trend. And in fact, I've never done this before, but I think I can. See if this will work. It's a line. Okay, there's this kind of curvy. Of course, mine's not perfect anyway because I drew it on a computer. But there's a line that you can kind of visualize and see that it fits the data pretty well. It's not perfect. And in fact, if you look at some of these years, so for example, from 1984 to say 1989, clarity went up. It got better. Do you see that? But in general, the clarity's gone down. We've gone from around 29 meters to be able to look down into our lake, all the way to around, it looks like maybe 21 meters. And that's a pretty big drop. Do you see that? But it doesn't drop every year, it goes up and down, but there's a trend. And this chapter is all about studying trends. Okay, and it could be by time, and it could be by two variables that aren't time. Okay, and we'll see examples of that too. Any questions so far? Okay, so that's what we've got. And again, this was a big deal. And when Bill Clinton saw this, by the way, unfortunately, he was a president that understood statistics. Okay, which I'm in big favor of. All presidents should understand statistics. And it's not true of all presidents, as you guys may know. But it was true of Bill Clinton. He was a very bright guy. And he said, aha, we have a regression line, because that's what we call this. And the regression line is telling us a story, and we can use it to make predictions. So the first thing is, if you look at this, and I'm not going to do the full equation. We'll do an equation later with the calculator and stuff. But first thing is, when you think of a line, what two numbers do you think of associated to that line? From basic algebra.
Negative
Very
one.
basic. Huh?
-1 and 1.
I'm talking words for the numbers, though. What words do you think of when you think of a line and the equation of a line? When I say it, you'll say, of course. Okay, slope and y-intercept. Does that ring a bell, I hope? It better, because it's a requirement for this class that you know how to handle equations of lines. And this week we're doing big time equations of lines. Nothing fancy, we're not doing logarithms or anything like that, but there's a little bit of algebra in this chapter. Okay, not too horrible. So slope and y-intercept. And the first thing is, for this particular example, the y-intercept is kind of useless. Okay, the y-intercept is useless. Notice that the data only goes from 1968 to 1998 here. Do you see that? So if you go to 0, that's too far in the past to even try to make predictions about based on a line. Do you agree? And if you think about society, it was totally different. And if you're trying to think about how the lake has changed based on human developments, it's very difficult to talk about far history. Is that clear? Okay. The slope, on the other hand, that is worthy of talking about. Do you guys remember how to find the slope of a line if you have a line? A couple important words or a few words. What's the general way of talking about the slope of a line? Finding it.
Rise over run.
Good, rise or run. Okay, again, you are required to know some beginning algebra, and rise or run is really important when it comes to lines. So notice if you go from 1968 to 1998, then our rise went from around 29 to around, if you look at the line, it looks like around 26 or so. Okay. So sorry, so it goes from not 29, it goes from about 31 to about 26. So it's gone down 5. Is that clear? I know, remember, you got to think upside down because it's upside down on the y-axis. So it's gone, so the rise is -5. And what is the run? From 1968 to 1998, what's the run?
30.
30. Okay. So what we can say is the slope is about -5 over 30, right? Which you can use a calculator, it's about 1/6. Okay, and we're doing things in meters. Meters are the way you do science, by the way. So if you don't know, a meter is about 3 feet, about a yard. So what that says is the way we can interpret the slope of this line, what we call the regression line, is for every year on average, the clarity of the Lake Tahoe has gone down by 1/6 of a meter, which is about 1/2 foot, 6 inches or so. So the clarity of the lake has gone down 1/6 of a meter every year on average. Does not mean every year it goes down, but on average it goes down that much. Does that make sense? Okay, so again, there's a lot of basic algebra in this particular chapter, especially about lines. So you are responsible for remembering slope and y-intercept. Okay, if we were to try to interpret the y-intercept, then that would mean the year 0. But the year 0 is ridiculous. If you know anything about Tahoe, do you know what the population of Tahoe was in the year 0?
No.
0. There are no people living here. It's too cold. It's too cold. You would starve to death in the wintertime. Does that make sense? We had some Native Americans coming in the summer, but it doesn't make any sense, so you don't even try to use it. Does that make sense? Sometimes you do use it, because sometimes 0 does make sense in particular data sets. But in this case, it's not very relevant. Is that clear? Okay. So what we can do, for example, is you could predict, based on this line, what the lake clarity would be today if the trend continues. Is that clear? So if that trend continues at about, again, 1/6 of a meter a year, and we're going from 1998 at, what did we say? This was about 20, looks like about, what did I say, 21. So if it's 21 meters and went from 1998 to 2018, that is 20 years, right? 20 times -1/6 is -26, right? Or a little more than 3 meters drop in clarity from then. Do you see that? So we're talking about this lake would be murky and not so pretty. It would be horrible. So based on this regression analysis, actually, Congress spent about $300 million and really did a whole lot of work. Congress didn't, but the Forest Service and different agencies did work to improve the lake clarity to make sure that people weren't destroying the lake. Is that clear? So again, you can use this line to make a prediction, but that doesn't mean that we know the future. It means that we worry about the future. And if you make changes, you can change the future. You guys, hopefully you all know that, right? So in particular, I'll share the screen on what really happened. And actually, before I do that, I think I want to talk about one more thing before I talk about what really happened, and that is R and R squared. So R is called the correlation. Have you heard of that word before? Two things are correlated, and by how much? So R is always between -1 and 1. So in particular, the sine of R is the same as the sine of the slope of the line. So it may not look like it, but the slope of the line is negative because y is upside down here. So R is negative. The closer to -1 it is, or the closer to 1 it is if it's positive, the tighter it is to the line. So if R is -1, it would be perfectly on a negatively sloped line. Is this perfectly on a negatively sloped line? The data?
No.
No, the points are not on a line, but they're not that far from 1. So this might be, this R is around -0.9. It's pretty close to -1, but it's not there. Is that clear? If R is 0, for most situations, you ever, I don't know what it's like in Modesto, but can you see stars in Modesto?
Depends where you live.
Okay, come to Tahoe. We have beautiful stars. And is there a linear pattern of the stars? If you look up, do you see a line of stars, or do you see stars all over the place?
All over the place.
All over the place. And maybe in Modesto you don't see any stars, so sorry about that if you don't know what a star is. But Robert, where are you from again?
San Jose.
San Jose. Yeah, you don't see any stars there either. It's too light, right?
Yeah.
But you've probably been like maybe to the mountains. And you can imagine what the night sky is. So the night sky is an R equals 0. It's a bunch of dots all over the place. Does that make sense? This is not what the night sky looks like in Tahoe, at least, because the dots are not all on a line, okay, or all even close to a line. They're just all over the place. So if R equals 0, then that's what it's going to look like. Any questions on that? If R is 1, then they're perfectly on a positively sloped line. And if R is close to 1, then they're close to being on a positively sloped line. Is that clear? Okay, so this is like a -0.9. Okay, the next thing you want to look at is something called R squared, which is, it's not a tricky thing. If you want to find R squared, you take R and you square it. And one thing, if you take a square, the negative goes away. You guys know that from math, I hope. Square of the number is always positive, so you don't have to deal with negative numbers anymore. But it's actually deeper than that. So let's say R was -0.9. R squared would be about 0.81. Do you agree? 9 times 9 is 81. And the negative goes away. And you want to think about that as a percent. So in this case, R is around 81%. So let me explain what that means. And this is very abstract. But I'll do it with an example, and that helps take away some of the abstraction. So if you look at the points, okay, if you look at the y values, which is the clarity, the number of meters for this particular scatter plot, then the y values vary pretty much. You'll see they go all the way from around 20 to around 32 or so. Do you see that? Okay, and they're just spread out. And the standard deviation of that is pretty high. Is that clear? Like a standard deviation of around 4 or so. It's a pretty big standard deviation, big spread out data. If you just ignore the year, do you agree? Okay, on the other hand, if you look at, say, just a year at a time or a few years at a time, then you don't get that vertical spread anymore. You see that? If you cluster here, over here at the beginning, or a little bit farther up, or towards this year, then you're only talking about a few years at a time. A few meters. Is that clear?
Yeah.
So we'll see the standard deviation has changed if you look at all the data with just ignoring the year, from like 4 to actually about 80%, 81% less than 4 on average per year, okay, per cluster of years. So there's been if you look at just 1-year areas, then you have a reduction of the standard deviation compared to just looking at all the data completely. Is that confusing? If you say no, then you're probably lying, because most people find this really confusing. Okay, so the idea is if you have a low standard deviation, you have a lot of precision on your guess on what the clarity is, for example. If you have a high standard deviation, then knowing the mean doesn't help much because it could be anywhere up and down. So if you have an R-squared of 0.81, that means that knowing the year really helps you on having precision on what the clarity is, the number of meters you have, versus just saying what has been the clarity over the last 30 years or so, all over the place. Do you see that? But if you just look at a small area, it's not all over the place. It's reduced by 80% in its variation. Does that make sense? So R-squared tells you that percent reduction on average in the variation of the data if you focus just on one particular year versus just looking at the data of all years. Any questions on that? Any questions? So Sabrina, thanks for coming, by the way. All right, so that is the main things about regression analysis. A couple others are, one, as you used to, there's a hypothesis test. And you want to find out if you have statistically significant evidence to say there's a correlation that's not 0. And if you have a correlation that's not 0, then that means that doing regression analysis is helpful. And using the line to make a prediction is useful. If you have a 0 correlation, the line is useless. Don't even try. Does that make sense? Okay, so for example, if you wanted to look at, I don't know, let's say the football game score at Modesto High School, if there is one, versus the number of tourists that we have in Lake Tahoe on any given day. Do you think they have anything to do with each other? No. That correlation would probably be 0. The dots it would just be a bunch of dots like the night sky. And you would never want to use regression analysis to try to predict what the football game score in Modesto High School is based on the temperature in Tahoe. I'm sorry, the number of people in Tahoe, number of tourists in Tahoe. It'd be just stupid. Do you agree? But trying to predict what the clarity is based on the year that you're looking at is very useful. Do you see that? Okay, so that's what our H0 is and an H1. H1 is that there is a correlation. And R is the variable you use for correlation. So the Greek letter for R, any of you guys know that? Called rho, R-H-O. And it's like a curly P looking thing. I'll show you it in a little bit. So we're looking at, and maybe I can write this actually. See how we're doing. So we can write H0. And so it's a curly looking P thing. So we say that's rho equals 0. So that means that there is no correlation. And H1 and that is rho is not equal to 0.
And that's saying there is a correlation?
Yeah, there is a correlation because you have a non-zero correlation. Do you see? Mm-hmm. Being non-zero means there is one. If it's 0, it's a nice guy, which means it doesn't help at all to use the year. Do you see that? Mm-hmm. It's hopefully obvious to you that the p-value will be really small in this case. Because just by just eyeballing it, is there a clear correlation? Is there a clear trend?
Yeah.
Yeah, there's a clear trend. This p-value will be probably, 0.00001 or something like that, because it's just clear. Sometimes you get a p-value that is borderline, but if you get a p-value of 0.8, it's over. Okay, now it could mean that your sample size is too small. You've learned that, right? But often it means that there's just no correlation. That's one or the other. Any questions on that? So I figured I'd tell you what the full story is of this particular data. We'll just do it for a second. You may not notice, but I cut off the most recent years to show you what really happened. And this one. Wrong one. One more time. All right, this is UC Davis's real website, which I didn't cut off. And notice what happened after year 1998. Okay, after year 1998, what happened to this?
It stops becoming linear.
It's not, yeah, now there's no correlation. It's just up and down and up and down. Do you see that? If you look at the year between 1998 and 2018, knowing the year doesn't tell you anything about the depth of clarity. Do you see that? So that would have zero correlation. Notice the slope of that line is zero. See that? Once you look at the most recent 20 years or so. Okay, and the reason for that is they did something. Again, Congress put in, hundreds of millions of dollars to protect the environment of this area. And the main point was to keep that trend of losing clarity from continuing. And it made all the difference. Any questions at all on this example? Any questions? Okay, I like it. This is my favorite example because it's near and dear to me. I know you're not from Tahoe, but it's our town. But Thomas, you said you've been many times, so you care too. Is that we do not have a muddy, smelly lake. But if they didn't do anything, if they didn't look at the regression line, which I know our President of the United States did, because this picture was shown to him, we wouldn't have had a zero correlation from that answer. Any questions on that? Okay, and these ups and downs, they're weather related. Weather does a lot of stuff for clarity, but I'm not going to get into that. That's a different class, not math. Any questions on regression analysis just in general before I give you a more not real example, but good for kind of questions that you're going to see on a test? Okay, but this is real life, and real life regression analysis happens everywhere. All right, so let me go and we'll do an example question. Let me find that. Right. Should be that one. I haven't copied it. That's why I'm having trouble. Just a minute. Okay, so here's the question. It says, suppose that the equation of the regression line that models the relationship between the amount of time, X in hours, a person practiced shooting free throws and the percent of successful free throws, Y, is given by, it didn't copy it, sorry. Let me type it out then. That's weird. Sometimes copy and paste doesn't work. I wonder if I can, let's do this. It's given by, let me write it out. Y, and usually put a hat over it, which means the predicted Y value is equal to 14 plus 0.4 x. Okay, and the correlation was found to be 0.85. So first, interpret R squared in the context of the study. Okay, and again, I consider, and most students do, by the way, that interpreting R squared is the hardest part of this whole chapter. The rest is actually not that bad. Okay, so what we can say is if you just look at general people and their free throw percent that they would get. Do you guys know what a free throw is in basketball? Do you know what one is?
Is it when you're on like the line and you just have like a free shot?
Yeah, it means that there's a foul committed, you get to shoot it in the hoop and you try to shoot it in the hoop. That's all it is. So I realize that I have some people that don't know what that is, and that's understandable. But don't worry too much about it. It just means a point that you get that after a foul. That's all that matters. Okay? And it's hard to do it because you have to shoot it in the hoop just perfectly from far away. Okay? And so we want to interpret R squared. So let's do that. There's going to be a lot of writing on this. So I recommend taking notes so you practice the writing too. Okay, so what we could say is that let me write in general actually. There is a large variation in free throw percent for the general public. So you just look at people in general without noticing how much they've practiced. For me, for example, my free throw percent would be really low because I suck and I haven't practiced. And I don't know if you guys about shooting a ball in the basketball, I mean a basketball in the hoop. Maybe I'm sure you do better than me because I really suck. But there's some people that practice all the time and they do great, right? So if you just look at people in general, it's all over the place in terms of free throw percents. Is that clear?
Yep.
Okay, but if you just focus on, or you just look at people who have a specified number of hours practiced. So if someone has practiced 10 hours, then you look at all the people who have practiced 10 hours, and you're going to have a different variation, and it's going to be reduced. Then this variation on average is reduced by, now R squared, again, if R is 0.85, what's R squared? Basic math, you got calculators? I never take away your calculator. So what's R squared?
I got 0.7225.
7225. I like to use two decimal places because then you can talk about percents. So about 72% by 72%. So notice that's a pretty big reduction. Do you agree? Okay. The other 28% can be explained by other factors. Or factors other than practice. And that might be how tall you are, for example, right? Or just your own genetic coordination, or I don't know, culture, who knows? By the way, I'm not a basketball expert, but it works well. So take a look at this. Is there any questions at all on this explanation of R squared? Because it is the most confusing of all of the parts of this particular chapter. Are there any questions? I think it's good to read this a few times. Even more important, could you do one of these yourself? With a
So they'll all be pretty much like this with just different based on the problem?
Yeah. It always talks about the reduction and the variation. You could also use standard deviation if you want. That's fine, because standard deviation is a measure of variation, right? So you can use standard deviation. Books usually use variation, so I'm using that word. Our book uses variation. Any questions on this? But don't just memorize it. Really try to understand what it's saying. Another way, a good visualization is, let's say you walked into an elementary school, say kindergarten through 5th grade, right? Call kindergarten 0th grade. And you look at the height of the kids. They're going to be all over the place, right? You got those cute little kindergartners, really, really short, right? And then you got the 5th graders that are, I mean, not as tall as you, but they're a lot taller than kindergartners, right? So if you look at the grade versus the height, there's going to be a big variation in heights if you just looked at the elementary school and didn't, just some general meaning in the elementary school kids. Do you see that? But if you walked into a 3rd grade class and looked at their heights, then you're going to have a lot less variation. Do you see that? Do you agree?
Mm-hmm.
So you would have a high R squared if you looked at X being the grade and Y being the height. Do you see that? Not every kid's going to be the same in 3rd grade, but you're definitely not going to have the same variation if you had all kindergarten through 5th. Can you visualize that? So I like that example because it's really easy to kind of imagine. Do you agree?
Yeah.
Okay, especially if you ever walked into an elementary school, because they're all over the place. The little 5-year-olds are a lot different than the 9-year-olds. Okay, any questions on this? Okay, now the next question is, remember I promised that this is the hardest, so now it's going to get a lot easier. Okay, use the regression line to predict the successful free throws through percent for a person who has practiced 40 hours. What do you think you have to do? The hint is it's easy. Any thoughts?
Did you say the y hat was the given y value?
The y hat is a predicted y value. So what do you think you have to do? The hint is it's easy. But you might need a calculator, depending on how good are you on mental math. Any thoughts? Any guesses?
Just plug in the 40 hours.
Yep. Yep. You take 40, you plug it into X. So let me just do that in. You take the 40, and you put it right there. And tell me what you get. I could do it in my head, but you probably can't.
Is it 30?
Yeah, 30. So for part B, 30 hours is our best prediction. So let's write this out. So the answer is 30. Sorry, 30 hours, 30% is our best prediction. So does that mean that if somebody practices, like for me, I never practice, but if you had me practice for 40 hours, I'm going to move up to a 30% free throw percent. Is that what that means? And the answer is no, since you're being quiet. Okay, you can't say that. The problem is, I am going to. That's the wrong grammar. You can say I'm predicted to, but you don't know that it's going to happen. You can only make a prediction. Do you see the difference? Okay, it's just like in the late clarity, you can predict what the next year is going to be, but no one knows the future. Do you agree?
Yes.
There's no way you're going to know exactly my free throw percentage, but you can predict it would be 30 hours if I practice. I mean, 30% if I practice 40 hours. Is that clear?
Mm-hmm.
So be careful about your verbiage. Don't use words like it will happen, it's going to be, it caused this. That's another one that's really bad. Okay, is that clear?
Yeah.
Okay, so now let's do part C. And that says interpret the slope in the context of the study. So first thing, general math question. Here's our line, y hat equals 14 plus 0.4x. You guys remember how to read this line and tell me what the slope is? It's easy, that's a hint.
Does it have anything to do with y equals mx plus b?
What's that?
Does it have anything to do with y equals mx plus b?
It's, yeah, I'm just looking for a number. Very simple. You got a 50-50 chance, that's a hint. How do you get the slope of a line if you see an equation? Remember? It has to do with y equals mx plus b. It's the number in front of x. Does that ring a bell at all? So
Yeah.
the slope is 0.4. That's algebra, okay, which is a requirement to know some basic algebra. And the slope is 0.4. So first, that's not the interpretation, but if you don't know what the number is, you have no chance. So slope is 0.4. That's from beginning algebra. Is that clear?
Mhm.
Yes.
Okay. And I'm going to adjust it a little bit. So I'm going to write down, and I'm going to use the letter that you're used to. Maybe I'll do it in a different color because we just used blue. And I am going to write down m, because that's what you're used to writing, equals 0.4 divided by 1. Do you all agree that's okay to divide by 1? And I'm doing that for a reason. I asked you a little while ago on the other example, what is the slope in a few words? How do you describe it in words?
Rise or run.
Rise or run. Okay? So if you write as a fraction, you can see it as rise or run. Okay? You can write as 4/10 also, or 0.4 over 1. There's different ways of writing the fraction, and it all is fine. So now we're going to think about what is the rise and what is the run. Is that clear? Okay. Again, rise is 0.4, run is 1. But what does that represent? So if you remember, the rise is how much y changes. Do you remember that? Because the y-axis, when you have an xy axis, the y is the up and down axis, right? So the rise is how much up and down you go. So the 0.4 is how much y is changing. Do you see that? So in words, from the original paragraph, what does y correspond to? It says in words, what is it?
Successful free throws.
Yeah, let's go free throw percent, right? So that says that we have an increase of 0.4% in the successful free throw percent. Do you see that? And then we have x is 1, and what is x? Read that paragraph.
Hours.
How hours a person practice shooting?
Hours a person practiced shooting, right? So what that says, now we can write down in words what this all means. And what we can say is for every additional hour, so if you want 1 hour, right, a person practices shooting free throws, on average, the free throw percent goes up by 0.4%. Any questions on that? Any questions? Okay, so does this mean that if you practice another, if I make you practice for 1 hour, that your free throw percent is going to go up by 0.4%?
No.
No.
No, remember the language. You can't say it's going to happen. Okay, you can't use an if-then with causation. All you can say is, if we look at people who throw an extra hour, practice an extra hour, there's a tendency to have an increase of 0.4%. So I know it sounds like a wishy-washy way of saying it, but you have to say it that way. Causation is never okay in statistics, okay? Unless you're using what's called a control study. I'm not going to get into that here. But basically, you can't use causative words. You can't do an if-then. All you can do is say, we predict that this can happen, or that we have a tendency for it to happen, or a trend of it happening. But you can't say that if you do this, this is going to happen. You see that? So don't make that mistake in the final exam, because I will give you the opportunity, I promise, to demonstrate that you understand the language you need to do to make this interpretation and to make sure that you avoid causative words. Is that clear?
Yes.
So please take that opportunity, or I will take off points on your final exam. Okay, so now let's interpret the y-intercept. All right, so first thing, from basic algebra, haven't been successful yet when I've used those words. What is the y-intercept? I'm looking for a number.
14.
14, good, good. At least I got one. 14 is the y-intercept. That's really important that you know your basic equation of lines. So the y-intercept is 14. I like to use it as a point. So if we're looking at the y-intercept, then we can write that as a point on the graph. The point has two numbers, right? For the y-intercept, what is the x-coordinate of the y-intercept point always? Beginning math.
0.
0. So 0, 14. Any questions so far?
No.
Okay, so unlike the slope is always useful as long as it's non-zero and as long as you we're able to say that we have a large enough sample. The slope is always useful. The y-intercept is not always useful, but sometimes it is. So the first thing is look at these numbers 0 and 14. See if they make any sense. Does it make sense for x to be 0? So again, x is the number of hours someone has practiced shooting. Does it make sense for someone to have 0 hours practice shooting?
Yes.
It does. In fact, do any of you have 0 hours practice shooting?
Yep.
Yeah. Okay, that means you've never shot. You never tried shooting a free throw before. Does that make sense? So that makes sense.
Yes.
Does it make sense to have a 14% free throw success? Can it happen? Yeah.
Yeah.
Yeah, if I asked, if this were a number instead of 14, if this were -4, it would make no sense at all. Do you see that? Because you can't have a -4% free throw percent success rate. Do you see that? Or if this were 190, also doesn't make any sense because you can't have 190% free throw percent. So you want to look to see, do the numbers even make sense? And sometimes they don't. Sometimes they don't for practical reasons. Sometimes they don't because it's just stupid. Okay? Like having -10 hours of free throw practice. You can't have that. Does that make sense?
Yes.
Okay. The other thing, and we don't have data here, but if you have data, you have to make sure the number 0 is not that far from the x values that were looked at. So in the example with Lake Clarity, 0 was too far away from the x values, so you wouldn't use the y-intercept. Is that clear?
Yes.
But here, we don't even show the x values, but at least the numbers make sense. So now we can predict it. We can interpret it because it does make sense to have a 0 and a 14. So now we just write down what it means to say x is 0. And that means that we have 0 hours of practice kind of an easier way of saying that is if someone has never practiced, right? So if someone has never practiced shooting free throws, then our best prediction for their free throw percent success rate is 14%. Any questions on that? Notice the words best prediction. What you cannot say is that if somebody has never practiced shooting, then their success rate will be 14%. Don't go there, because you don't know every individual. There's a spread of all the people. Does that make sense?
Yeah.
But your best prediction is the 14%. You could also say on average. But best prediction I like a little better. So there's different ways of saying it, but there's a lot of ways you can't say it. You can't do the if then, you can't do will happen, you can't do this is causing. Those are bad words in this subject. And I should mention, there's a word that you should pretty much never use in this class, and that is prove. So if you use the word prove on your project 2, I will take off points. Okay, you never, hypothesis tests never prove anything. Got it?
Got it.
So what they do is they provide evidence for something, but they don't prove it. So I'll see that a lot on these, just like we never prove anything by looking at this data. All we do is get predictions. Do you see that? Statistics is all about making predictions, good guesses, but never about proving something happens. Any questions at all on that?
No.
Okay, let me do another example, and I'm going to do some of it because, again, I could just repeat example over example of the same type, but I don't think that is what that's not what the webinars are about. I like to show like a main highlighted example of the main things that we're doing. So the next thing is, how do you get these values? How do you get R? How do you get the equation of the line? You know, what I told you. And the way you get it, and this is what this class is all about, is what? What do you always have to do to get values of statistics first? Tell as I delete all of this and put a new one in. And then you'll see when I put a new one in.
Get data.
Get data, exactly. So, oops, didn't kill it all. Missed a tiny bit. So let me give you another example that has data. Okay, which I made up, but you know, in the real world, you get data. All right, so notice the second word, data. So the data below show the results of a study of 9 community colleges done that looked at the percentage of students at the community college who receive financial aid and the percent who are business majors. Does that make sense?
Uh-huh.
Okay, and let's consider these being California community colleges. Got it? Just to make life easy and more relevant to all of us, because we're all connected to California community colleges, right? Because you're taking this class. Okay, and conduct a hypothesis test for the correlation, then perform the full regression analysis. Okay, so the first thing is we've got to conduct the hypothesis test. How do you start when you conduct a hypothesis test? What's the first thing you write down?
The null and alternative hypothesis.
Exactly, the null alternative hypotheses. And the good news for this particular chapter is they're all exactly the same for anything you have to do. And I wrote one of these for the late clarity one. You guys remember?
Did the H not equal 0?
Well, there's an H naught, so let's start that out. So definitely H naught, so that's a good start. H naught is never equal anything. H naught has a colon after it. And then remember I gave you a funny letter that was Greek?
That was the P, it was row.
Yeah, row, row, row your boat. Just remember that. And it's not a P, it's a row. It's row equals 0. Any questions on that? Okay, and then H1. And do you remember what that one was?
Does not equal 0.
Yeah, row does not equal 0. So if I give you on the final exam to perform the regression analysis for, a hypothesis test for regression analysis, you have no excuse because it's always this. It never changes in our class, at least. Okay? Because that just says, do we have 0 correlation or do we actually have a correlation? If you don't have a correlation, basically you stop saying anything because it doesn't help to have a line. You shouldn't even talk about it. Does that make sense?
Mm-hmm.
You can guess if I give on the final, do you think there's going to be a correlation?
Yeah.
Yeah, because I'm going to want you to do all the rest of the stuff, right? Because otherwise you just quit. Okay, so that's a hint on the final, by the way. If you get a p-value that's high, you should worry a lot. It's a correlation problem. Okay. So the next thing we do, and I recommend you do this also, is get your calculator out. And you're used to doing this, is get the data into your calculator. Let me go and pop in the calculator, which is one version of the TI-84. Okay. And what you do when you're used to this is we're going to go to Stat. We're going to Edit. We need L1 and L2, so you need to clear out L2. And we need L1, you need to clear out L1. Any questions so far? And then L1, you just type in your financial aid data. So we had 42, and then 38. If you don't remember, that's okay. Just trust me. I'm looking at it. 56, 19, 40, 37. And we had 72, 55, and 20. And then L2, that was the business major data. And that was 15, 17, 7, 34, 12, 15, 6, 9, 27, and that's it. Any questions about typing in the data? This should be old hat for you guys, because we've done that in other chapters for different reasons, right? Now, also should be old hat, you hit the Stat button. Then we're going to go to Tests. Again, you're used to that. Now, we're getting towards the end of the course, aren't we? Which means we're getting to the bottom of the tests. So here's a suggestion to make life easier for you. You don't have to do it, but it's easier. If you use the up arrow instead of the down arrow, it'll go to the bottom. And what we want is lin reg t-test. And all of your calculators should have that. Any questions so far? It's very easy to do in the calculator. I hit enter. And XList, if it doesn't say L1, you need it to be L1. And that would be second 1, but mine already says it. YList, you need to be L2. And that would be second 2. Freak is always 1. We need a not equal to, so hit enter on not equal, because that's our hypothesis, right? Our alternative hypothesis. Don't worry about reg equation. That's if you want to just graph the scatter plot, which you won't have to do. And then enter. And it gives us everything. So you'll notice the p. What is the p-value, by the way? Tell me the number.
5.02.
5.02.
That's what I was worried about. That's not the p-value.
Point 0.0005.
0.0005.
I see that.
Okay, and Robert, how'd you get that? How'd you fix their problem?
Just move the decimal over 4.
Yeah, the E-4. Pay attention. P-values can never be a bigger number than 1, right?
Yeah.
So
Right.
worry, get that. So if you ever get a p-value bigger than 1, it's wrong. Got it?
Okay.
So it means you're not looking far enough to the right and you're not seeing that E-4. And that's not just for regression analysis. That's the entire course, by the way. We've had a lot of p-values already. Okay, so don't forget that, please. So the p-value is 0.0005. Okay? And I'm going to write this down because I lose my screen after a little while. So the p-value is 0.0005. And then if you look, you'll see where on the top it says y equals a plus bx. It's a little bit confusing because you're used to mx plus b. So the easiest is just put in the numbers and then you can think mx plus b. Because the b is actually opposite on the calculator. Sorry about that. But I'm not from Texas, so I didn't put the Texas Instruments calculator program in. So, and you'll see A is about 36.9. I'm going to call it 37 just to make life a little easier. So it's 37 plus, and B is about negative 0.5. So that's minus 0.5x. So our equation is y equals 37 minus 0.5x. Any questions on being able to read the calculator? Okay. By the way, it uses a t statistic, same t as you had before. We're not going to do much with it, but it's that same t when you did a t-test. And the rest we're not really going to use. Any questions? Actually, there is some more that we're going to use. I should say that. If you go down, forgot about it. R squared is 0.84. And R is negative 0.92. About. Any questions on the numbers? Okay, so now we can go back to our question. And that was this one. So we have a p-value of 0.0005. I'm hoping at this point in the class, you know what to do when the p-value is that small. What is it?
It's not. There's a correlation.
One more time?
Would it be that there's a correlation?
Yeah, but there's a couple words that we always use for any hypothesis test.
Reject or fail to reject.
There is statistically significant evidence. Do you remember that?
Yeah.
Remember those words? So I do want you to put those words in. So let's write this out. There is statistically significant evidence to conclude that, and now we state H1 in words. There is a correlation between percent of financial aid majors, not majors, percent of students who receive financial aid and the percent of business majors at the college. Any questions on that? Any questions? Okay, just a note, if you remember, the y-intercept was 37. Is it relevant here? What do you think? Okay, it helps to write out the point. 0, 37. Do these numbers make sense? Can you have x equals 0 at a California community college? What do you think? There's 115 California community colleges in California. Any ideas? Maybe you don't know our system. The answer is no. Every college has financial aid students. Do you believe that? No college is even close to having every student being so rich that they don't need financial aid. Okay? So whatever college you're at, it's normal. Okay? At our college, Tahoe is really poor. So there's lots and lots of financial aid students. But even in the wealthier areas, there's a pretty significant percent of financial aid students. It doesn't even make any sense to say no financial aid. Does that make sense?
Yes.
So in this case, the y-intercept is not useful.
Okay.
It's also, the lowest number you see is 19. That's nowhere near 0 either. So you wouldn't even use that. The slope, on the other hand, which was negative 0.5, that's always useful. And especially because it's always useful if there's significant evidence. And you can say that for every percent increase in financial aid financial aid students, on average, there are 0.5% fewer business majors. Does that make sense?
Hmm.
Does that mean that if we give more students financial aid, they're going to change business away from major? They're going to change majors away from business? What do you think?
No.
Absolutely not. You can never say they're going to. Does that make sense?
You can predict?
Yeah, you can predict, okay, or you can say there's a trend of 0.5% decrease for every additional percent of financial aid, but you can't say it's going to happen. If you give more financial aid, you're going to lose business majors. You just can't say that. Is that clear?
Yes.
Okay. Let me give you a secret word. Again, I've touched on all the main points for this particular chapter. So let me give you the secret word. I'll do it in red because it's important and bigger. It always does that to me. One more time. There we go. And the secret word is variation. Remember, R squared was all about the variation, the percent decrease in the variation, if you know one variable based on the other one. Any questions on that? Any questions? So again, I want to remind you, you should really be focusing on your projects. Projects are a big percentage of the grade, so make sure that you post on the Project 2 discussion forum if you're ever confused about something. I try to respond as promptly as I can. Won't be every 10 minutes, but pretty often. If a day goes by without me responding, you should worry about my life. Because I don't think that's ever happened, unless I tell you in advance. I don't think that's even happened. But I do plan on hiking on Saturday. I'm going to do a 24-mile hike.
Wow.
So don't expect me to answer really fast on Saturday. Hopefully that'll work. There may be too much snow, but if there's not too much snow, we're doing a 24-mile hike with my friend and I. So if there's a lot of time on Saturday, I don't get back to you. I'm out in the wilderness, having a great time. But we got to do that. Got to have good times. Okay. Yesterday, I did a 10-mile hike just in the evening, just a few hours. I'm a really fast hiker. So just to know that if I don't get back to you like in 3 or 4 hours, I'm in the wilderness off the grid, enjoying myself, which you got to do. But I will be in the morning and evening. I'll definitely be checking. Okay. And there's no big weather predicted, so I don't think we're going to lose electricity, and I won't be able to get back to you on that. You know, those are other reasons. So, are there any questions about anything?
No.
I have a question about the project, actually.
Okay, sure.
So for the assumptions, I know you said don't confuse it with like the central limit theorem. So are the assumptions just like basically like normality, like assuming that the population is like well represented, and like just stuff like that?
Population is what? Sorry, I didn't hear you.
Well represented.
Yeah. See, remember, if you haven't, not if you have, you must have, unless you're one of those that's collecting special data where you only have a small amount of data. But if you're doing a regular project, you must have over 30. So you don't need to assume normality because you've got it. Does that make sense? Over 30 gives you normality. But most of you are doing convenience sampling. That's fine. Okay, it's not fine, by the way, if you're doing some kind of research project in a specific field. But for this project, it's fine. Just say that you did a convenience sample, so therefore there's going to be bias involved. Does that make sense? Mm-hmm. Admit to it. I don't take off points for convenience sampling, but I do take off points if you don't admit to it. You should always be honest. That's important, because honesty is important in life. Okay, does that make sense? Mm-hmm. So those are the main assumptions. Sometimes things come up and there's going to be assumptions. Sometimes like people got confused about the question, so you're assuming they answered it correctly, depending on your projects. Does that make sense?
Yeah.
And that does happen. Like, I don't know if no one's doing it, but in the past people have asked like, you know, how many servings of vegetables do you eat every day is one of the questions. And the problem is people don't know what a serving is. And that would be an assumption, is that people answered accurately. Okay, so depending on your project, some projects it's obvious and they know. If you ask how many siblings they have, they're going to answer out honestly. No one's. Well, I'm not sure how many siblings I have, or most people at least. Does that make sense?
That makes sense.
Yeah. So for some projects, there's assumptions on accurate answers. And just know, real data is often not clean. So I saw a post, I don't know if it was one of you, but I saw a post where some people didn't answer the second question. If that happens, you throw that data out, those people. Because you can't have just one answer to a question when you're doing a dependent samples test. Okay, and that's real life. Real life has data issues. Other questions? Okay, please post recommendations on when you want next week's webinar to be. Because this is our first Wednesday one. We had 3 people, so that was okay. I'm hoping that we have lots next week because I'm reviewing for the final. That's kind of important.
Okay.
So that one's, so please post, not just 3 of you, but everybody. Hopefully others are watching between now, because I usually like to make the decision by Friday morning for sure, usually by Thursday night, but maybe by Friday morning this time, we'll see.
Okay.
Is that the last one?
What's that?
Is that the last webinar?
Yeah, that'll be the last webinar of the quarter, because I don't do a webinar finals week because some people take the final on Monday. So having a webinar after you take the final doesn't mean anything. So that's why it's the last one. I talk about the final exam, and hopefully it goes well. I also talk about ANOVA for the first 20 minutes or so. It's a short, easy section. Okay, other questions?
No.
So if you don't have questions, we can say good evening. But I'm always happy to answer questions.
Thank you, Larry.
All right, thank you, Sabrina.
I just want to make sure I got. So my confidence interval for the project
Mm-hmm.
at 95%, it was about between -3 and then -4 for the bounds.
Uh-huh.
So meaning the original score is between the mean is between -3 and -4 points less than the after score. I think is
Yeah.
what it's saying.
Exactly. And you usually want to use the word less instead of negative. If
Okay.
you say it was -3 more than, just sounds awkward, doesn't it?
Mm-hmm.
It's a lot better to say it was 3 less than.
Okay.
Yeah, so you're right about that in kind of wording it so that it sounds a lot better.
Yeah.
Because this is a written project.
Yeah.
Yeah, so that was good. And then of course you want to look at that and say, is it worth going to 90%? Take a look at what the confidence interval would have been at 90% and see if that would be worth the sacrifice of losing some confidence by having it narrower. Does that make sense?
Mm-hmm.
And if you're using my spreadsheet, it's really easy to change it to 90%.
Yeah.
You don't have to type enter. You just type 90 point, and then it'll just do it for you.
Yeah. And then I watched the video on the standard error. Any heads up on what we need to write about that?
Well, one thing is make sure you include it by itself. And again, the standard error itself gives you an idea of how accurate your estimate is for the difference between the two variables, because you're estimating the population mean difference. And if your standard deviation is large, then that estimate's likely to be a poor estimate. If the standard deviation is small, then that estimate of the difference between the means is likely to be a good estimate. Does that make sense?
Yeah.
So that's one thing, is that in the standard error, you're definitely looking at the standard error itself. Then you should also include it in the confidence interval. So if you are satisfied with the width of your confidence interval, so if it's giving you good information, that I forgot was -2 and -3, I think, or something he said.
-3 and 4.
If that is informative on helping make decisions, because now you know it's somewhere between 2 and 3 less for the before than the after, then you should be satisfied with the standard error in terms of the confidence interval. If that's not informative, if that's kind of too big a spread, you'd like to narrow it out, but don't want to sacrifice your confidence, then having a larger sample size to decrease the standard error would be recommended. Does that make sense?
Yeah.
Okay, then for the hypothesis testing, it happens in 3 places. Basically the whole project. For the hypothesis testing, if you got a small p-value, like 0.0002, you're very satisfied. Do you agree?
Yeah.
So so in terms of the hypothesis test, you're satisfied with standard error because it gave you what you wanted. If you got a large p-value, like 0.89, you're also satisfied because it helped tell the truth to give up. Do you see that?
Yeah.
If you got a standard error like 0.06, and you're using, let's say you're using a 5% level of significance, then you're really frustrated.
Yeah.
Because you still think you're right, but you're not able to say it. That's the worst, right? And in that case, you would say that the standard error is too large. And if you raise the sample size, you can decrease that standard error, and that will set the p-value either much lower, so you're going to be able to say you're right when you were, or much higher, so you'll know to give up. But you're not ready to give up because you missed it just by a little bit. Does that make sense?
Yeah.
Does that help some?
Yeah, it does.
And remember, it's all about the difference. It's not about the individual. The whole project is about the difference.
I don't think that we have anything on the individuals specifically at the moment, like it's fine.
Yeah, you don't need anything on the individual.
Okay.
The only thing that you might mark on the individual is if you had a severe outlier for either individual,
Uh-huh.
then you might want to remark about that because that messes up data. Does that make sense?
Yeah.
So if you asked, how many hours did you sleep last night, and I don't know, how many calories did you eat the next day? And somebody said, I ate 12,000 calories. Then you might want to mention that. Does that make sense?
Yeah.
Because that really changes the whole data set.
Yeah.
That's kind of the only main individual thing is if you have something that's really a big outlier for either data set, then you have suspicions that the whole test, all of the confidence interval and the hypothesis test may not be very valid. Does that make sense?
Mm-hmm.
Otherwise, the individual is not what you're writing about. You're writing about the difference between the two. That help a lot?
Yeah, it did.
Okay, good. Thomas, any questions?
I kind of have a question that's still regarding the standard error and the hypothesis test.
Uh-huh.
If we have a large p-value, then we're going to be satisfied because we're just going to give up on the whatever we're doing.
Yeah, you're not happy, but you're satisfied. Do you see the difference?
Yeah.
You're not able to show you're right, but at least it's to give up. And that's important. It's really important to know when to give up, right? Whereas if you have 0.06 and you're using 0.05 for level significance, you can't say you're right, but you're not wanting to give up. Do you see that? That's like the worst. But if you got 0.9 for your p-value, you're giving up. Bigger sample size is not going to make you right. Does that make sense?
Yeah, that part makes sense. I'm just kind of trying to still wrap my head around how it's related to the standard error.
Okay, so the standard error, a small standard error makes the truth appear. Because remember, the standard error is all about the reliability of your data. So if you have a small standard error, then your data is reliable and it's going to show the right stuff. It's going to show the truth. Whereas if you have a small standard error, your data might be far from the truth, the population. Does that make sense?
So a large standard error will show the truth?
No, a large standard error does not show the truth.
Okay, so
A small standard error shows the truth.
Okay, that makes sense.
Yeah. So the p-value being very large or very small gives you the truth. A p-value on the borderline, just above the level of significance, doesn't give you the truth.
Okay.
Does that make sense?
Yeah.
Because then you're just not sure whether you're right or wrong. You're hopeful still, but hopeful is not the same thing as having evidence. Do you see?
Mm-hmm.
And that sucks because to do another study, you have to tenfold your sample size. You're not allowed to do another study with the same sample size because actually your probability of a type 1 error increases every time you do another study with the same sample size, and that's never okay. But if you have a much larger sample size, then your probability of a type 1 error is going to be tiny because you have a large sample size. But it's exhausting to have a large sample size, right?
Yeah, definitely.
So that's kind of what's going on. Does that help?
Yeah, that helps. Thank you.
What's a good standard error number?
What's that?
What's a good standard error number?
It all depends on the units. Like if you were doing height, then if you're doing it in, say, inches, maybe a 1/4 inch. Do you see what I mean? Because that tells you kind of right where the difference is. If you got 12 inches for height for standard error, that'd be horrible. Because that means you're fluctuating by a whole foot in people's height. And that's just doesn't tell you anything. Does that make sense?
Yeah.
So it depends. Okay, but if you were using meters instead of inches, then everything changes. Then you're going to need a standard error of like 0.005 or so, because 0.005 meters is still, a little bit of, right? But a half a meter is that much. Do you see that? So there isn't an answer what's a good standard error. It really depends on your unit system and what you're interested in measuring.
Okay.
Any other questions?
I think I'm okay.
Okay. And Robert?
I think that's it.
Okay. And again, you can always post on the Project 2 discussion forum for those questions, or Q&A for other questions. Okay, and request for time Q&A format.
Okay.
Okay. So if you're okay, we can say good night or good evening.
All right. Thank you.
All right. Thank you, guys. Thanks for coming. And for all of you who are watching this as an archive webinar, thank you very much for watching. And don't forget to post on the Q&A forum. And if you have questions, general or Project 2 discussion forum, if you have any questions about the project. And don't forget, by this time next week, you should really be sending me your information on where and when you're going to take the final. And hopefully by tonight, you'll be sending me your rough draft so tomorrow I can evaluate it and let you know where you can improve. So have a good evening. Goodbye.